Assalamu alaikum guys. So today is our second lecture of first week, and in this lecture we will talk about basics of radioactivity and some other basic stuff from the radioactivity. So towards the end of the 19th century, minerals were found that would darken a photographic plate. It's a very famous incident, even in the absence of the light. And this phenomenon was later on discovered and called radioactivity. And Marie Curie isolated two new elements that were highly radioactive, and they are now called polonium and radium. So radioactive rays can be of three types: alpha rays, beta rays, and gamma rays. And in this lecture we will understand their basic uh, phenomena. Alpha rays are basically nuclei of the helium atom, and they are heavy as compared to beta rays and the gamma rays. And the alpha rays uh, are not so much ionizing, and they can barely penetrate a sheet of paper, and they can be stopped by just a sheet of paper. And in which the phenomena in which we get the alpha rays is called the alpha decay. So the second one is the beta rays, and in the beta rays, beta decay, we can have three types of beta decays: beta plus decay, beta minus decay, and electron capture. And the beta rays are more penetrating than alpha rays, but less penetrating than the gamma rays, and they can penetrate the 3 millimeter of the aluminum sheet. The gamma rays are highly energetic, and it's difficult to stop them, and we have to use some dense material like lead, of course of few several centimeters to stop it. So if you have a gamma radioactive samples, so we have to use some lead box in which we should place it to save the other environment and the humans. So how we can detect these radioactive rays? It's very easy. If we have a magnetic field, we can do it. And in the magnetic field, we can see in the right figure. In this figure, we have all three kinds of samples within the lead blocks, and you can see the alpha particles, alpha rays and beta rays are moving in different directions within the magnetic field, and opposite to each other, which means they have different charge. The alpha particle have different charge as of beta particle. So they are charged particle also, and the gamma rays are moving deflected, which means that it has no charge. So gamma rays are just like our electromagnetic radiations, like X-rays or radio waves or some other electromagnetic radiations, but of high energy. So in the next slide I will show you the basics of alpha decay. Alpha decay occurs when the strong nuclear force cannot hold a large nucleus together. In the figure you can see the parent nuclei is decaying via alpha decay, and we have a alpha particle in the outgoing particle, and we can see by the conservation of A number and the Z number and the N number, we have A minus 4 for Y and Z minus 2 for electrons for the Y daughter nucleus, and helium is the alpha particle. The mass of the parent nucleus is greater than the sum of the masses of the daughter nucleus and the alpha particle. This difference is called the disintegration energy. So this is the example of alpha decay. You can see the one example in which one parent nuclei. Ra is decaying into Rn, and it has less A number and less Z number, which Z, as we already know about, it shows the number of electron or number of protons, and A is the number of total nuclei, means number of protons and the number of neutrons. So in the coming lectures we will learn about deeply about the alpha decays and the beta decays and the gamma decay. So alpha decay is can be explained by the quantum tunneling process. In the figure you can see the alpha particle can penetrate the potential barrier if even if it has less energy than the Coulomb barrier, the height at 10 fermions. And this phenomena cannot be explained by the classical physics. It can be explained by the quantum tunneling process. So if the particle have energy less than the Coulomb barrier, still we have some alpha decay, and this is similar to cluster decay, in which an atomic nucleus emits a small cluster of neutrons and protons, and the details and the calculation will be done in the coming lectures. So quantum tunneling was first introduced for alpha decay by George Gamow in 1928, and some other scientists. They have solved the theory of the alpha decay by using the quantum tunneling concepts, because it was not possible to understand the process by classical mechanics, classical physics. They assume that the alpha particle and the daughter nucleus exist within the parent nuclei already, and namely the decay of the quasi-stationary states. And the quasi-stationary state is defined as the long-lived state that eventually decays. Means it is the state or the alpha particle which is already formed in the parent nuclei, has some energy, but this energy is less than the Coulomb barrier, and it cannot escape from the parent nuclei according to the classical physics, because it has less energy. But still we have alpha decay, which can be explained only by quantum tunneling. It means that it has more transmission probability of alpha particle if it has more energy. So classically it is forbidden to escape, but according to quantum mechanics it has non-zero probability of tunneling through barrier and appearing on the other side to escape the nucleus. So these scientists calculated the penetration probability of the alpha particle to the Coulomb barrier, which we will learn in the coming lectures. The main success of this model was the reproduction of the semi-empirical Geiger-Nuttall law, which is very famous, not included in our lectures in our course, and it must be noted that the other common forms of decay, beta decays, are governed by the interplay between both the nuclear force and the electromagnetic force. So thank you, students. This was just introduction of the radioactivity. In the coming lectures we will focus on more detailed analysis. Thank you. Allah Hafiz.